Our presenter for today is Dr. Anders Blom. He received his PhD in theoretical physics from the Lund University in Sweden in 2003. In 2004, he joined Atomistix as a sales engineer. He was also part of the core group that founded Quantumwise in December 2008 to take over the activities from Atomistix, which included the development of the electronic structure and transport simulation software called Atomistix ToolKit. Today, Anders heads the sales, marketing, and support department in Quantumwise. He is a specialist in applying atomic scale modeling to advanced semiconductor devices. And without further ado, over to you.
Okay, I hope everybody can hear me. I'm very happy for the invitation to present the webinar. Actually, this is my first webinar, so it's kind of exciting for me. It's kind of a pity I can't see you all because it would be nice, but I can see that there are quite a few attendees, so I hope you'll enjoy the presentation. We will also be hosting this on our website later on the film. So the outline of the talk is shown here. I will be speaking about, as the title said, nanoelectronics, and quite specifically, a lot of the examples you will see throughout the presentation are made with our software. But I don't know the background of everybody, so I've decided to make this a rather general presentation as an introduction to nanoelectronics, if you wish, but in particular where we as a company and through our customers see the field of CMOS nanoelectronics heading via the publications that are coming out, via the conferences, the presentations, and so on, because it's quite an active field and it's quite an exciting field, but it's also a very uncertain field. So is nanoelectronics here? Well, maybe it's coming soon. Definitely it's coming sometime because everybody wants nanoelectronics to succeed. We know the benefits of it, the low power consumption in the devices, better performance, everything, but there are certainly very formidable challenges in getting nanoelectronics to work in practice. So what we will be looking at in this webinar is how modeling simulation on the computer can help nanoelectronics become a reality, and we will look at the methods that are necessary and a little bit about how our software is hopefully helping in this area. And at the end, you will be able to ask questions, which I will be very happy to answer. So if we take a look at a very old slide by Mao presented in 1998, it's clear that already at this point there was an awareness that scaling, as we have known it, where computers just became faster because the clock frequency of the CPUs was increased, would come to an end. We then saw the rise of the multi-core, and again, if we trust this prediction around next year, that actually also comes to an end for various reasons, power consumption being definitely one of them. And so by 2010, we should start to see new devices. Are we then seeing new devices? Do we have nanoelectronic devices in our computers today? Well, it depends on how you see it, I suppose. And the way Intel sees it, definitely we do, because they are now at 22 or 28 or 32 or 45 nanometer node, depending on the chipset in your machine. And you can call that nano. It's 22 nanometers. But on the other hand, the actual transistor technology in that chip is traditional. It's a traditional transistor. It's based on a large amount of electrons, and you don't really have the nanoscale effects that we'll be discussing here. So in that sense, it's not really nanoscale. So of course, the search for new nanotechnological devices has been going on for a long time. And again, this is a slightly old slide, and I like to show it because one thing you can see is missing here, which is graphene. So new technologies can also arise very quickly. Hopefully they will stay. We can see here nanotubes probably was thought as a very valid contestant for certain nodes, say 5 nanometer. It might still be, maybe graphene will be the choice, maybe another technology will rise. It's very difficult to predict, especially the future. And I find it very interesting to see how, as I mentioned, graphene was not even on this slide, but today it's one of the most active research fields in the world. And but the thing which definitely is happening is that silicon, in some sense, is coming to an end. Maybe not completely. There'll definitely be a lot of uses for silicon, but it's not going to be by itself. Already today, we have the hafnium dioxide in the high K dielectric in the transistors, in Intel's solutions, in Intel's chips. And what we're looking for the coming decades is essentially the entire periodic table is now on the table. No pun intended. And germanium is a very serious contender for the p-channel MOS, and you have the 3,5 materials, indium gallium arsenide, and now we're also seeing all the other two-dimensional materials, not just graphene, but MOS2, molybdenum disulfide, boron nitride. So the complexity definitely increases here, as they say in this slide, exponentially, and it's now another decade of materials discovery we have entered. So what does nano really mean? I said that we are not really in nanotechnology yet, so how do we know that? Well, nano means small. Okay, we have small transistors today. They're 22 nanometers, and in fact, when you look at even a 45 nanometer SRAM cell, as in this slide, it's amazing how small they actually are if we compare to other small things in our bodies, such as this red blood cell. So definitely nano means small, but if we're really talking about nanotechnology or nanoelectronics, there must be something more. And what it in particular means when you go small is that things become quantum. The laws of motion of electrons is no longer guided by Ohm's law, but instead we have quantum effects. So what does that mean? Well, it is very simple. Picture, if we look at this electron, the red lines are supposed to be the electron bouncing around in some material. And if this was now a large, sort of classical, macroscopic piece of silicon or whatever, the electron is bouncing around, it's being accelerated by the electric field, it bounces on various impurities, it's scattered, and in the end, there's some sort of velocity, an average velocity by which this electron is transported, and from that we can calculate the usual device parameters like the resistance or the mobility and these types of classical quantities. And we use Ohm's law to describe how the circuit works. But in the nano device, which is indicated here by the black little box, if that is actually smaller than the so-called mean free path, which is the distance the electron travels between scattering events, then this entire picture breaks down, and instead we go to this quantum regime. We no longer have a classical resistance, which depends on the length of the device, but in fact is length independent. And if we look at when does this breakpoint occur, it's for metals, and silicon is about the same actually, especially highly doped silicon. You end up with a number around 16 nanometers. So if we are looking at transistors, which are today 20 to 40 nanometers, we are actually coming below this point. We are more in a mixed zone. We're not in the completely deep quantum yet, but when we go to 12, 10, 8, 5 nanometer transistor nodes, definitely the picture will change. And for instance, something like mobility might no longer be the relevant quantity to discuss. And this is something which is sometimes very difficult for device engineers to get used to. Okay, so suddenly the mobility is not my parameter of measure of sort of quality index of this channel. There's something else. Well, things like interface resistance and so on may be suddenly much more important. So what happens to current when we go to the quantum level? If it's not described by Ohm's law, then what is it? Well, in a ballistic conductor where, as I mentioned, the electrons are actually not really scattered, they don't have time to scatter during the time during which they travel from source to drain, if we take a transistor perspective. Then instead, current is in fact a propagation of the wave function, the electron wave function. And you have constructive interference, you have scattering events, still you have scattering, but it's some sort of potential scattering instead. So it's coherent and it's also elastic. So the electrons do not lose momentum and they do not lose energy as they traverse the gate region. So how do we calculate the current in this case? How do we calculate the current from a propagation of a wave function? Well, this is actually relatively well-established formalism. It was developed several decades ago by Landauer and Büttiker, and you can find this expression in standard textbooks, which are studied in most undergrad or grad courses in universities today, where you can calculate the current from just the transmission probability, the probability that an electron will travel undisturbed from source to drain. Now, this is the quantity called T here, capital T. Now, the main problem is actually computing this. The formula is easy enough, but if you really look carefully in literature, they don't really tell you how to calculate this transmission for a realistic device. Of course, we can do it for toy models, but now we're talking about a real device with atoms. It's three-dimensional. There are perhaps impurities. We're applying electric fields both across and along the channel, and actually computing this transmission is the key task for device modeling. And this is, if I may jump to sort of the product part of this presentation, which won't be that long. That's what our software does, in fact. So, but that's one effect of small. It means that we go quantum. The other aspect is quite naturally that we now have to consider each and every individual atom in the system. Now, this can be a blessing, or it can be a curse. It's usually a blessing in the sense that it means that we can design the functionality very specifically. So if we imagine that we insert some molecule between two metal surfaces, then this system has some particular properties that we're very interested in, and we want to design the device according to these properties, and they are a result of these particular atoms. But you can also imagine that if an atom now is out of place, is knocked out, or if this is now a more sandwich type material where we have some oxide between two surfaces, if we introduce defects, vacancies, then individual atoms can also cause the entire functionality to disappear. So treating this becomes very critical as the device size approaches the nanoscale, and understanding it in particular. And you may want to consider this question. How many dopants are there actually in a 5 nanometer transistor channel if we dope it at 10 to the 19 centimeter cube? 5 nanometer transistor channels are supposed to come to the market around 2020. And if we just follow the sort of traditional way of introducing free carriers in a semiconductor device, we should dope it. But in that transistor channel, there will be less than one. So statistically, you might have one, or you might not have one. Now, that is not a very good situation to be in, because you won't be able to control the device across sort of a wafer or across a batch of samples. And this in some sense was observed already quite early when the silicon oxide gate leakage problem became abundant. If you have only 1.2 nanometers of silicon oxide, it can't really block the leakage current anymore in the gate stack. Now, this was solved by the introduction of high-K dielectrics, which are actually thicker than 1.2 nanometers. They're usually in the range of 3 nanometers. But if you really want to dope the channel and have free carriers because of thanks to that, then at these short channel lengths, that might not actually be an option. And I will come back a little bit to that later on. So how can modeling help here? Well, it's no secret that modeling can help. Cleverer people than me have said it well, as in these quotes here. And of course, you wouldn't dream today of designing a car or an airplane or even a computer chip, of course, without doing modeling. The question is what type of modeling, and the question is what quantities we can actually compute. And modeling, of course, has been used in the design of materials and even devices for a very, very long time. So if we look at the traditional way that modeling is applied in the so-called TCAD market, then you kind of separate it into two areas. You either simulate the materials or the devices, but not really as a combination. Now, how does that work? Well, if you're looking at the materials, it's basically all silicon, first of all. So that makes it simple. You can use any material you want as long as it's silicon. The unit cell is usually very small. You can understand the material on a very fundamental level through various levels of accuracy. And there is, for instance, one very strong success story for, in fact, first principles modeling. When the 45-degree rotated silicon substrates was introduced, that was a result which increased the performance of silicon CMOS quite substantially back in the 2000s. This was a direct result of first principles modeling at Texas Instruments. And we need more success stories like that, of course, for the future. That would be very nice. On the other hand, the devices are very elaborately simulated. There's a whole hierarchy of TCAD tools in the EDA business, of EDA tools, and at the lower bottom we have TCAD, and then you have chip design, and so on and so on. And modeling has been extremely successful in this area, but you are really simulating sort of continuum processes, like I mentioned. The current is described by Ohm's law. You can include various types of physical effects, almost like a finite element type simulation. And you do this really in continuum. So you don't really care about the atomistic structure of the device. Everything is described by bulk materials, so you know what the conductivity of silicon is, you know how that might depend on strain, and so on and so forth. Now, this picture really changes now, because now the device is becoming so small that we really have to look at the individual atoms, as I mentioned before. We have to start introducing quantum effects, and this fundamentally changes the way we simulate the device. In fact, the device is no longer just a sort of a collection of bulk pieces. That's the old type of device. You have some area of p-doped silicon, then you have another area of n-doped silicon, and you know how to cleverly connect these two. But if you take a look at, say, a bilayer graphene structure or a gate stack like on the bottom right here, where you have hafnium oxide, silicon oxide, platinum, then it's not so clear where one material begins and another ends, because of course the wave functions will extend throughout the entire system, or at least into the neighboring regions. We're now looking at new elements. We have perhaps graphene, we have hafnium, we have tantalum, titanium, germanium, molybdenum, who knows. The parameters for these materials are not known, but what is even worse, it's not bulk hafnium you have in there. It's not even bulk hafnium oxide. It's a very, very thin slice of hafnium oxide. And that will not have the same properties even as bulk hafnium oxide. And then you put this hafnium oxide on top of silicon, doped silicon, whatever, and now you have another system. You have the combined system of the two materials, which again behaves differently. And this poses enormous challenges. Also, the optical, mechanical, and electrical properties actually become more or less intertwined because they're all the solutions of the same quantum mechanical system. So this is the challenge before us, and we will now look into a bit more what we can do to address this. So going back just a little bit to the question of why would we be doing this? I mean, there's a lot of experimental effort going on. People are seriously studying these structures with lots of elaborate measurements and so on. So what role does modeling have in this? Well, one of the things is that on the nanoscale, it's actually very difficult to do experimentation. It's expensive. It's rather difficult. It takes a lot of time. You're dealing with expensive materials. You have to take, for instance, wafers out of your production in order to do measurements on them. That's rather expensive by itself. Those wafers could go to production instead. But even worse, when you're looking at the quantum effects, the probes that you are coming in with onto this very, very small device are actually of the same size as the device itself. So it's not even certain that you're measuring an intrinsic property of the system. You could just be measuring, just as well be measuring, if you imagine an AFM tip coming in and pushing around atoms, are you measuring just the atoms, or are you measuring the AFM tip plus the atoms? So the influence of the instrument is very strong, and you also can't just look at the system with a microscope and know exactly where your probe is located. It's very difficult to know what property you're actually measuring and what system you're really looking at. Well, of course, modeling is not that easy either, especially at this advanced level where we want to take all the quantum effects into account. But what we're definitely seeing is that the TCAD models are falling behind, and there's a large gap here to bridge in terms of which materials can be considered and what physical properties, or rather what physical effects, are included in the models. The the win here, the potential win, of course, if we can complement TCAD with some sort of atomic scale modeling, is that we're not going to throw away TCAD completely. There's, as I said, there's a long chain of models that derive from TCAD, but one possibility is that we can start introducing new parameters and these new effects into the TCAD models from the atomic scale calculations. And at least when we are talking to companies, we're trying to convince that they should be doing more modeling. We try to point out these facts that you can get a better basic understanding of your materials. You can get some ideas what might work, what might not work. And actually, computers are, in some sense, cheaper than people, and it's quite easy to automate and parallelize computations. So that's a good sort of setting point sometimes. So one of the catchphrases in this game is actually the interface is the device. You'll see that popping up a few times. This was originally said by Herbert Krömer, the Nobel laureate, in a very succinct way. And recently there was this article in Nature Materials saying the interface is still the device. Well, to some extent, I might change that a little bit and say the interface is finally the device. And today we are really seeing this explosion of new types of devices based on not, as I said, individual materials put together in various blocks, but the actual interface between the materials is the device. If we take the copper tantalum, for instance, here, driving the current through this interface has markedly different effects than if you just have copper or just have tantalum. In the nickel silicide example here, what happens when you start introducing various dopants at the interface is that you can tune the Schottky barrier. I've already shown the gate stack on the bottom right. We can also see a very interesting grain boundary, twin grain boundary in, well, I think it's supposed to be copper in this case, in this middle picture here. I'm sorry, I'm not sure if you can actually see my mouse, but you can see the grain boundary in the middle there. And at the top middle, there is also a model of a silicon oxide interface. And you can clearly see that there's no way you can describe the properties of these materials by just taking, say, silicon and silicon oxide, and calculate them separately, and then assume that you can sort of just merge the properties. You have to study the system as a whole. Here's a specific example on this, published a few years ago. There's a long-standing contact issue in silicon carbide devices. The question is it an ohmic contact or is it not? So these are TEM images of epitaxially grown titanium silicon carbide on 4H silicon carbide substrates. And as you can see from the TEM image, this is an amazingly ordered and atomically sharp interface. The red arrows indicate the interface. But the question is now, the interface can actually trap a carbon layer. And this has been shown to modify the Schottky barrier. So the question is, can we, with modeling in some way, understand this? So we introduce two different models. We compute the case where we have a silicon-silicon interface or a silicon-carbon silicon interface. And the results of this study is very clear. If you take the silicon-silicon interface, there is essentially an ohmic interface. There's a small slope of that of the dots, the blue dots, but definitely for the silicon carbide silicon interface, we see a very clear Schottky barrier. My mistake. That should be the other way around, of course. So silicon carbide, silicon carbon silicon is a ohmic contact. And I thought that the authors of this article put this statement very well in the article, that thanks to modeling, they were able to shed new light on processes that were going on at this buried interface, which is so deep inside the structures. There's no way you can measure whether you have actually that carbon layer trapped. But knowing now that we can relate the Schottky barrier, the ohmic behavior versus the Schottky behavior, to the existence of this carbon layer, that gives us new insight. So what are the properties that we should compute then? I kind of alluded to the fact that, okay, Ohm's law is no longer valid. We don't talk about the resistance of a material, even the mobility might not be relevant. That's a contentious approach, I know, statement, but at least when we are studying nanoelectronic devices, the quantities that should be computed are quite different compared to the traditional DFT or other types of atomic scale modeling. So for instance, when we're talking about ballistic transport, the relevant quantity is not mobility but conductance. The conductance does not depend on the length of the system, as the resistance does, but rather the electrons are transported coherently and without scattering. Without, I should say, losing energy and momentum. They can scatter. Scattering just means that you get transmission less than 1, so that's what gives you the conductance. We can compute the Schottky barrier, as we just saw in the previous example. The leakage current is, of course, a very interesting quantity. If we have a thin slice of material that is either supposed to transport the current or block the current, as in the case of the gate stack, then it's very important to know how the leakage current depends on, say, the presence of interface, defects, peak defects, various charge states, and so on. In a bulk material, you would calculate the band structure, and this would tell you everything. In tunneling type devices, you actually rather calculate the complex band structure, and you may not have come in contact with that before. What you see on the top right is the complex band structure of a silicon 100. So the complex band structure is directionally dependent, as actually is the band structure, of course. So taking that a Ka, Kb, the two first Brillouin zone wave vectors equals 0, we see then actually see the usual conduction band minimum at the far right is kind of a white dot actually. But what you see on the left are the complex bands. These are the bands which are decaying, but if you have a thin enough slice, then they actually have a chance to carry a small amount of current to the other side. So if you have a thin slice of silicon between, say, two metal electrodes, some of these complex bands will give you a tunneling current across, even in the band gap, as you see the red sort of semicircles connect the conduction valence band. So there are states in the band gap. They're just evanescent. But if the slice is thin enough, they may actually propagate. A very, very key quantity to a lot of the properties in the nanoelectronic world is the contact resistance. I kind of mentioned this also before, that it's not so much determined by the actual mobility of the channel, but most of the performance is determined by the contact resistance between the source, the channel, the drain, and in some sense even the gate. So what we see on the lower hand right figure is an example calculation we did last year on the contact resistance between nickel and graphene. You see the nickel is green, the graphene is gray, and we computed the contact resistance for a graphene sheet, an infinite graphene sheet in the plane, in the screen plane, lying a little bit on top of a nickel. And you can see on the far right, the colorful plot is the current density for a particular mode. So that's a type of quantities you can extract. Is rather visual, and one of the conclusions of this study was in fact that the contact resistance doesn't really depend on how far you overlap the graphene with the nickel, because the current, the electrons, essentially transfer from the graphene into the nickel right at the interface, right at the contact point, and then very little current sort of remains in the graphene on nickel. So then it doesn't really matter how much they overlap, you will always have the same contact resistance. So this has in fact been correlated with experiments. And of course, you also would calculate all the usual quantities such as effective masses and band gaps and so on. That's just part of the standard computational set, if you wish. But coming back to the question that I have talked about a lot, that we're not in bulk anymore. We now have to look at the interfaces. I have three pictures here of rather different kind, just to show you on the top left that gold, we all know what gold looks like, but actually when you make nano gold or colloidal gold, as you see in these bottles here, the color changes with the size of the particles. These are gold colloidal nanoparticles. And that's the message I'm trying to bring across. Like if you have a very thin slice of silicon oxide or hafnium oxide or strontium titanate embedded between two other materials, those also have radically different properties depending on the size, depending on the contact, depending on the bonding, depending on the particular way the crystal is oriented and so on. So you cannot just take the bulk quantities and translate them to the nano world. And on the right-hand side, we can see, for instance, a very clear example where you take two insulators, but the interface between them is conductive. So that is highly unintuitive and unexpected. And really, of course, you can try to measure it, but really, this is an area where modeling can provide a lot of insight and also try to help you find materials with this property. Won't be true for all kinds of interfaces between insulators, but by studying them systematically, you can try to find good candidates which otherwise fit in your manufacturing process and so on. And I haven't, by the way, that picture is from the same Nature article that I showed before. I haven't credited the left-hand side picture. I hope I won't get into trouble for that, because I actually wanted to raise a very important point here. The question marks here are inserted on these sort of metallic-looking electrodes that have been placed here, as well as on the substrate or on the dielectric SiO2. Because look, you're talking about some sort of MOS2 molybdenum disulfide monolayer here, and you can see the individual atoms. But what about the atoms in the drain? What about the atoms in the substrate and the dielectrica? You cannot separate the resolution in that sense, in that way. Those contacts will also be atomistic, and you have to consider that. You cannot just assume that they are some big slab of metal. Maybe for the sort of leading in the electrons into the device, yes, they will behave as usual metals, but definitely the contact between the MOS2 here and the contact will be of the utmost importance. So what choices are there? What type of nano devices are we talking about? Well, actually, it's a jungle out there. There are so many choices that it's in fact quite bewildering. And I think that is to some extent scaring the industry. They are looking at nanowires and carbon nanotubes, and now it's graphene, and there's boron nitride and molybdenum disulfide, and should it be graphene bilayers? Should we be doing something with iron magnesium oxide for memories? Actually, you probably should. Should we be doing molecular electronics? And what happens to silicon when we make it really small? There are so many questions to be answered in this area, and very little time to do it in fact. So I'm hoping that more and more people will help in this area, do more modeling, and try to answer these questions. Which of these device architectures are actually viable for future applications? And probably that the answer to that will depend on, well, which application are you talking about? Low power will have one set of rules, high power will have another, high performance. And when we're talking sensors and all other different types of RF areas, there will be different answers to that question. So maybe all of these are viable in their own space, but finding out is the trick. I talked about how few dopants you can actually find in a 5 nanometer, relatively highly doped, 10 to the 19 per cubic centimeter channel. One way to get around that is to actually say, well, forget doping. Maybe we don't need doping. I just wanted to sort of bring up this article, which was published last year, which takes an interesting approach to this. You can actually get a tunneling FET, field effect transistor, without doping by doing the correct design. We can see the gate all around. In the left picture, you see a gate all around metal gate, it's supposed to be the purple thing. I've removed it in the right-hand picture so you can see the nanowire. And this device is actually made out of tin, which is a semi-metal. And this is a very unique and quite exciting concept in my opinion. I hope they will continue their studies and other people will follow to consider this type of device structure. So, to summarize a little bit and to look at the commonality between all these different choices for devices and all the points that we we have talked about for the few, maybe the last 10, 15 slides. We are dealing with now exotic materials. There will be always some silicon and germanium, but really we have to consider the fact that we now have hafnium and tantalum and a lot of other materials in there. We are on the small scale, but we're still dealing with many atoms. It's not 1 or 2 or 6 or 10 atoms. It's several hundred, several thousand, maybe several tens of thousands. But we still have to consider the quantum effects, and we have to treat it atomistically because we have the problem with individual defects, and we need to treat the interface and so on. The interface is the device. What does that mean? Well, it means we need to consider things like boundary conditions. We need to consider advanced electrostatics. And all of this combined, all of this at once. So these are strong implications for the choices of methods and modeling techniques, and that's what I will get into in the next segment. So what methods do we have available if we want to study this? Well, you may have seen a picture like this before in various shapes. We can, of course, go to the highly accurate Hartree-Fock or GW type calculations where we can treat almost anything, but we can treat at most maybe 10, 20 atoms. So that's not really viable in this case. We need to treat a large system. DFT is a very natural choice in the sense that we can go to relatively large amount of atoms, and it still has a high transferability, meaning that we don't have to put in any empirical parameters. We know that we have some issues with semiconductors, and we'll get to that. But otherwise, we can basically treat any combination of atoms that we want, any type, any kind of molecule, oxide, metal combined with semiconductor, whatever. If we can't afford DFT in the sense that we need still more atoms, we can go to semi-empirical methods, and there are many to choose from. They definitely suffer from the fact that there are parameters for only a limited set of elements, and even worse, sometimes you also have parameters just for specific combinations or pairs of atoms. So you may have indium arsenide, you may have gallium arsenide, but it's pretty difficult sometimes to make indium gallium arsenide parameters. And if you want even more atoms, then you can go to empirical potentials. In that case, you don't get an electronic structure, but you may want to do molecular dynamic simulations. You want to look at heat transport, still on an atomic scale. And what would be ideal is if you have a tool that has all of these. And actually, that's what we have in our software package. And if you saw the change on the left-hand side, one of the really key issues here is that the predictability of these methods also increases. That's another way to say transferability. If we are looking at some semi-empirical methods that have been highly parameterized for, say, bulk indium arsenide, it's not certain that they actually are valid for a thin slice of indium arsenide, whereas the DFT you can probably trust more for that. So isn't it true then that DFT and particular LDA GGA doesn't really work for semiconductors? Well, actually, it works for some things. Forces and total energies, for instance, come out pretty well. So if you take the silicon 100 surface, LDA actually is good at predicting the geometric structure of this. And phonon frequencies generally come out pretty okay and so on. So DFT is not a total disaster for semiconductors. Of course, the band gap is an issue sometimes, but there are also new approaches to solving that problem. For instance, meta-GGA, this Tan Blaha from 2009 parameterization, which actually gives you a very, very nice band gap and band structure in general for germanium, which is completely hopeless if you use LDA and GGA. And in particular, what's nice is that the masses are good and you have a very reasonable strain dependence of the band structure as well. So this is promising. It's not a golden hammer. You can't attack everything with meta-GGA, but maybe silicon germanium would be reasonable to look at more in detail with meta-GGA. Okay, so the interface is the device. Okay, well, you understand what I mean. The interface is the device. So how do we treat interfaces? What type of software, what type of approach in terms of modeling can we use? Well, there are essentially two classes of software packages out there. If you just go look for them, you can find the types that study isolated molecules or those which study periodic systems. But actually, a device is something more, something in between that. Now look at the carbon nanotube with a molecule in between here. It's actually a combination of something periodic and finite. You have the gold pentacene system on the right. It's not periodic, definitely not in the C direction here, right? If you take the nickel graphene nickel system on the left-hand bottom, it's also a combination of something which is periodic and something which is finite, at least in one dimension. It's two-dimensional slab in between. So, and then we want to apply a finite bias across the structure as well, which breaks the boundary condition completely in the direction of the electric field. So what's the deal really here? Well, I made this at the very end of my preparations. Actually, what's difficult here is the boundary conditions. It's actually quite easy to solve the Schrödinger equation in a simple boundary condition, but when you get difficult boundary conditions, complicated boundary conditions, as in these systems, where it may be heterogeneous, meaning that the left-hand side is different from the right-hand side, or you apply the finite bias, or you have to combine something periodic with something finite, the boundary conditions is what trips you up. What we need is open boundary conditions, and we can see a very simple example of open boundary conditions in this from Wikipedia, and you've probably studied this in your university courses. You send in a plain wave, some of it will bounce, some of it will be reflected, some of it will be transmitted, and from the transmitted part you can calculate the transmission. And actually, that's essentially what we do when we study nanoelectronic devices using DSP. We applied, of course, a slightly more advanced simulation framework. We use non-equilibrium Green's functions to describe the transport because we have a non-equilibrium distribution of electrons in the middle. But the idea is the same. And I'm going to be slightly fast across a few slides here. If you watch this later on YouTube, you can pause and perhaps look at the slide in more detail. So the type of simulation that we do is a self-consistent cycle between the electronic structure and the transport. So that's what makes it more difficult than solving a usual DFT problem, because as the electrons are transported across the device, the number of electrons, in fact, in the middle changes and has to be computed self-consistently, as well as the entire electrostatic potential profile and all of the usual quantities that you would do in a self-consistent calculation. And in the end, when you want to calculate the electron current, you use the Landau-Pizzica formalism that I presented before, but now we actually know how to calculate the transmission. We could also note that, of course, a transistor is not a two-terminal device, it's a three-terminal device. So we also need to add gate electrodes, and that means you have to have an electrostatic solver that is capable of treating that type of boundary conditions, not just in the transport direction, but also in the transverse directions. We see an example on the bottom right with an indium arsenide nanowire, an indium arsenide thin type device, which has two gates applied, the bottom and the top gate. And you can see how we can tune the current by several orders of magnitude by sweeping the gate voltage. So as for the final few minutes before the question round, I just want to say a little bit about our company and also how you could be doing some of these calculations yourself if you're interested using our software. So Quantumwise is a relatively small company, but we are living entirely on providing solutions for atomic scale modeling to industry, government labs, and of course academic users throughout the world. We are around 10 employees, most of us located in Copenhagen, Denmark. We also have an office in Singapore, one in Japan, and we have sales representatives in several other countries like India, China, Korea, Taiwan, and the US. We have two kind of products, although they're baked into one software package. So one thing is a Nano-device simulator, basically, to compute all the results that you've seen in the previous slides. And the other is a more general atomic scale modeling platform with a nice graphical user interface that helps users be more efficient in using various types of modeling techniques for atomic scale. And that actually includes not just our own software, but it can act as an interface to other software packages as well. of the world in a sort of commercially engineered product, so not just sort of haphazard software, but really engineered through all the practices that are possible. And you can go to the website and you can have a look at the articles that have been published with the software. There are over 700 at this point, and you can search in this and you can get an idea what people are using it for and see if there's something that's similar to your interests. And a few final words about the graphical user interface, which we call the virtual nanolab. Now, we've been working on that for quite a long time, actually, and one of the problems that we always ended up in was that every single one of our users and every single area of simulation was slightly different, and it became really difficult to make one graphical user interface that could fulfill the needs of everybody. So we thought long and hard, and actually very fortuitously during the last few years when we've seen the rise of the apps in mobile phones, the Android system, in the iPhone system, but also plugins in, say, web browsers and so on. It came to us that actually the solution is to make a platform where we can add plugins that define the specific functionality. So we decided to make sort of a platform with apps or plugins for atomic scale modeling, and that is how our entire software functions. So essentially, it's a big toolkit of plugins, and you can add your own tool. You can, if you find space in that garage there, you can hang your own tool, meaning that you can develop your own plugin, and of course you can share it with other people. So if we take a look at our atomic structure builder, for instance, then the builder itself is just a driver, just a motor. And then all of these different functionalities for manipulating the structures, for combining them, for performing various operations on them, and also reading external file formats and writing external file formats, all of that is defined in plugins. So if you would like to import a file made in another piece of software into here, or you would like to export from here to another software form, another file format, you can write your own plugin that defines that import-output, import-export file formats. There are quite advanced builders. There are quite simple ones, like just deleting atoms or adding tags to atoms and so on. And there are quite advanced plugins like a crystal builder. There's also a cleaver and an interface builder. This is one of the relatively difficult problems as we want to build these devices, is how do we merge two different structures in a sensible way, make an interface between them. And really having the combination of a graphical user interface and a programming language, because ATK is based on Python, so everything is done in Python, both in the graphical user interface and the back engine. And the combination of these two really give you a powerful way to approach these simulations, because on the one hand, if you don't care about programming, you can do everything graphical, point and click. You can build the structures, delete a few atoms, insert them, take some graphene, take a nanotube, cap it, and so on. And then use the graphical user interface to define the parameters of the simulation and even run it, and then look at the results. And you don't have to worry about sort of complicated file formats or coordinate lists and so on. On the other hand, if you do like that kind of thing, you can automate your calculations. You can calculate quantities in a very advanced way for a large number of structures. You can loop and scan over, say, a lattice parameter, and so on. So on the one hand, it lowers the barrier. You can try more crazy things without spending too much time building the structures and so on. And on the other hand, and also learning the file formats and so on. And on the other hand, it also unleashes the power of data analysis here, because you really can do things very quickly that otherwise you would have to spend a lot of time doing over and over again as well. So this is kind of a picture of the universe of our simulation framework, where you would create models. You have them in a project, so you can manage the files. You can analyze the results, of course, run it. And let me just quickly wrap up with a little discussion about how we integrate third-party software in this as well, because the whole graphical user interface is not just an interface for our code, the Atomistix ToolKit, ATK, but also some other third-party software packages, like ABinit, for instance. We have actually fully integrated ABinit in the new version of ATK, which is coming out this summer. So you can set up ab init calculations completely in the GUI, completely as you would an ATK calculation. You can run it in parallel, and then you can store the results in easily manageable NC files, netcdf files. You can analyze them afterwards. You can plot the band structure, whatever you want, just as it was a native ATK exact calculation. There is also a VASP scripter, so you can produce the VASP files. Of course, we don't ship VASP, but you can read VASP geometries, you can create VASP geometries, and even create entire VASP scripts, so the in-car K-Pons, POTCAR, if you have them, files, and run them. And then also, coming up very soon, possibility to plot the band structure and look at the results. Our GUI and the whole software runs on both Windows and Linux. It's parallel as well. There is so much more I didn't have any time to talk to you about today. If you're interested, I'll be very happy to get in touch with you and tell you more about that. We have, for instance, a very interesting project on molecular dynamics coming up very soon, where you can do things like the bottom picture of a copper nanowire interconnect. But time is running out for today. So let me just say that if you are interested in trying ATK yourself, you can go to the website. The link is there. It's very easy to find if you just type quantumwise.com. And I'll be very happy to give you all a 2-month free trial. Normally it's 1 month, but if you write webinar, I'll make it 2 months. And you can find more resources on our YouTube channel. There are quite a lot of nice tutorials for the software there, and the website in general. So with that, I thank you for your attention, and I'll be happy to answer any questions.
Thank you, Anders. Audience, if you have questions, you can use the Q&A tab on your browser window to post your questions, and we'll have them answered. Okay, we have one question, and it reads, are you integrating Atomistix ToolKit with LAMPS for molecular dynamics?
No, we are actually using a completely other code package. It's called TremoloX. It's developed by the Fraunhofer Institute in Germany. It just has similar functionality as LAMPS. But we are also working very hard on developing new potentials. This is part of an EU project, and part of that project is to integrate this code into our platform so we can run, say, phonon transport calculations and so on. But another part is to develop new potentials, because if you look at all these different materials that we've been discussing today, silicon oxide or hafnium oxide, there are essentially no good potentials for those materials. And if you want to study them seriously for, say, thermoconductance and so on, we also have to come up with new ways to design potentials for them. That doesn't take 6 years to develop. Maybe they'll be quick and dirty, but at least they should be able to give some kind of insight, and that's the other part of the project.
We have another question. Do you have an example of ATK working with TCAD?
This is a kind of a new area. This is an emerging area. So one of the difficulties with working with TCAD is that some of the assumptions that they use don't necessarily hold. The very specific example is that many of the parameters that they desire, for instance, effective mass, well, the effective mass in a usual material is normally quite energy independent, at least at the bottom of the band. It may be anisotropic, but it's usually quite parabolic, the band. Now, when you take a nanostructure, you take an indium arsenide fin, which is just 8 nanometers across, for instance. Actually, it turns out that the subbands have, first of all, very different effective masses. They have very anisotropic masses, and they're very highly non-parabolic as well. So there are some challenges in this area. We are actually working with some TCAD companies to try to address that, but I don't have an example at the moment. I could show you band structures of these fins, and you can see how non-parabolic they are. But this integration with the TCAD tools, I would say that's a very active work in progress right now, but we don't have any results yet.
There's another question that reads, can ATK model non-self-consistent tight binding models?
Yes, we have a set of built-in tight binding models. Some of those are self-consistent, some of them are non-self-consistent. It's also possible to include your own tight binding model, again, self-consistent or non-self-consistent. So if you have in the literature a particular model, it can be DFTB, it can be state-across tight binding, non-orthogonal. Then you can actually insert those parameters into the software and run all the transport or band structure, whatever calculations with. So just taking your parameters and running them sort of with our engine. That's possible. So then you don't need to implement all your own matrix routines and band structure calculators and all of those things. You just bring us the parameters and we can do the work for you.
What is the learning curve for Atomistix ToolKit?
That's a good question. I mean, it's very difficult for me to answer, to be honest, because once you know it well enough yourself, it can be difficult to see. But of course, as a commercial provider, we help our users. We have tutorials on YouTube, video tutorials that show you how to build structures, and these range from very simple structures to actually very complicated structures, like a capped carbon nanotube and some interfaces between silicon and silicon nitride and so on. And then we have tutorials. If you go to the website, you will click on tutorials, you will find quite a few tutorials that show you not just how to build something, but also how to calculate relatively complex structures and then analyze them. And we probably in the future will we will arrange more webinars of this type, where we perhaps also do demos and real teaching of using the software.
Audience, we can take one last question if you have any. Okay, I think we have no further questions. Thank you, Anders, for the wonderful presentation, and to the audience, thank you all for logging in and listening to this webinar. We will be hosting more webinars in the future, both in Atomistics and on other topics as well. And as to stay updated on the same, you can log into our website, that is http://lns.umich.edu/NNIN-Michigan. Thank you all once again, and have a nice day.